To this presentation of constant pressure charts. So we're going to start out looking at kind of the general characteristics of constant pressure charts. We'll step through the elements, we'll show you how to flight plan, and then we'll look at examples. First off, kind of the general things about surface charts. These are, of course, observations of the upper atmosphere. And those observations are made by weather balloons, aircraft. Remember we talked about TAMDAR and AMDAR. That information makes it on constant pressure charts. At once upon a time, there were wind profilers across the United States. They have been decommissioned because of monetary issues with NOAA. So you don't see those there anymore, but there is satellite information that gets on constant pressure charts from GOES satellite and also POSE satellites. And you should know that, of course, these charts come out twice a day at 0Z and 12Z. And typically that's when radiosondes go up. So the bulk of the information found on constant pressure charts comes from radiosonde information. Here are all the radiosondes or the upper air observations that are made across the United States. In our neck of the woods, the closest to North Dakota is Bismarck, also International Falls and Aberdeen, and then down in the Twin Cities they also have Chanhassen. So those are the radiosondes or weather balloons that go up twice a day at 0Z and 12Z. You can see that typically the distance between stations is anywhere from about 100 to 200 miles. They set up that network that way. And what we're looking at with constant pressure charts, these are charts where, well, as the name implies, everywhere on that chart the pressure is the same. Now you know that pressure varies in the atmosphere. As you go up, pressure decreases. But if you send up a weather balloon and you note where it crosses a certain pressure level in the atmosphere, measure that height, and then look at another balloon, send up another balloon maybe 100 or 200 miles away, and notice where it crosses that pressure in the atmosphere, that height, and you'll see that those heights are different. So these constant pressure surfaces where the pressure is the same, isobaric surfaces, the heights are different. And the heights are different because the temperature is different. Where the air is colder, pressure surfaces are closer to the ground, the air is more dense. And where the air is warmer, then pressure surfaces typically are found higher above the ground. So the height difference in these pressure surfaces is what we're looking at on these charts. So these charts, typically these are average altitudes. Of course, altitudes may vary depending upon the temperature of the air. But generally speaking, we can find the 925 millibar level at about 2,400 and so on and so forth. The 850 is 5,000 feet. You should memorize these numbers because they're useful when you're looking at computer models, and also when you start looking at jet stream charts. It's nice to know what altitude the particular pressure level is. So most of us are flying right now at lower altitudes. We're flying little piston airplanes, and we're down in the 925, 850, or maybe even 700 millibar levels. If you're flying a turboprop, you're more likely to be about 500 millibars, and if you're flying jets, you're above 300 millibars. So the information that's put on these charts is either plotted information or an analysis. Remember, these are all observations. The station model on upper air charts is very similar to the station model on surface charts. There's less information. And then also, whenever we make observations of the upper atmosphere, we do that with respect to the metric system. So temperature and dew point would be in Celsius. The height of the pressure surface would be in meters. The wind, of course, is always measured with respect to true north, and the wind speed is plotted in knots using the standard barbs and half barbs and flags to indicate winds. The dew point is not always represented. Sometimes you'll see the dew point depression, and that's kind of challenging to figure out if it's the dew point or dew point depression.
If the dew point depression is 0, that means the atmosphere is saturated at that point and you're probably in cloud. So this is one way to help figure out if there's clouds at altitude. We use a rule of thumb that if the temperature dew point spread, if the dew point depression is less than 5 degrees Fahrenheit, 5 or less, then there's a high probability that there are clouds in that environment. Here are a couple of examples of station models from two different charts and two different sources. The one on the left shows a temperature of minus 19, and the green numbers 26, minus 26, would be the dew point, because you couldn't have a dew point depression that is negative. So that's one way to figure out if it's dew point or dew point depression. So that's your dew point on the left. On the right, here's a station model with the dew point depression. The temperature is minus 23, and you wouldn't have a dew point of 3 degrees Celsius. It would be approximately 26 degrees warmer than the temperature, and you can't have dew points that high. So in this case, it would be a dew point depression that they're plotting. It's 3 degrees less than minus 23, so your dew point would be 26, minus 26. And seeing that it's within 3 degrees, that indicates, or within 5 degrees, that indicates that there are clouds, more than likely in that location.
So that was the plotted information. As far as the analysis that's done, they do height analysis, temperature analysis, and wind analysis. In the height analysis, as we mentioned, the height of the pressure surface varies depending upon whether there's warm air or cold air in a given region. Where the heights are lower, we call that relatively lower heights, or a low. Where heights are higher, we call the relatively higher heights, or a high. And then we plot that on the chart. Generally speaking, as you move towards the North Pole, the air gets colder, so the pressure surfaces are closer together, and they slope down towards the North Pole. At the equator, the temperatures are warmer, so as a result, the pressure surfaces are farther apart. So that produces a sloping pressure surface from the equator to the North Pole. And we do an analysis of these heights on a constant pressure chart, and when we draw lines of constant height on a constant pressure chart, we call those contours. And these are heights MSL, typically measured in meters, because scientists like the metric system. And these are solid lines. Typically, these solid lines have labels on them to indicate the height of that pressure surface in decameters, which is 10 meters. So for example, on this 700 millibar map, you might see 300 on a contour, and 300 indicates 3,000 meters or 3 kilometers, and that's about 10,000 feet. If you multiply 3,000 times 3.28, that gives you about 10,000 feet. Notice that the heights get lower as you get towards the North Pole. As you move north, as you move south, they get higher. And then you'll see areas where they have relatively lower heights, and they'll put an L in that area. So the other thing you need to notice is that the change in heights, how rapidly does the height change? Where you see a rapid change in height, that's where you have stronger winds. In other words, the gradient, the height gradient, is a lot stronger. Where you have a very slow change, where you don't have many lines, then the winds will be weaker. So on this map, we plot highs and lows. Also, extended areas of relatively higher heights are called ridges. Areas of extended lower heights we call troughs.
An analysis of temperature is performed on all upper air charts. These lines of constant temperature are known as isotherms. They're plotted every 5 degrees Celsius. Looking at this chart, you can see the dashed lines that are blue and red indicate isotherms. And you have colder temperatures to the north and warmer temperatures to the southeast. Typically on this chart, where it changes from blue to red lines, that indicates an area where it is freezing. In other words, that is the 0 degree isotherm in that region. Another analysis that's performed is a wind analysis. It's also called an isotac, because isotacs are lines of constant wind speed. And depending upon the source of the charts, they use all sorts of different coloring and hatching to indicate isotacs. As a rule of thumb, they try and plot isotacs every 20 knots, and they turn on different colors every 40, anywhere from 20 to 40 knot change in wind speed. We will now talk about flight planning using constant pressure charts. Constant altitude charts provide you with an overview of your en route flying conditions. Depending upon the altitude that you're flying, select a chart that is very close to that altitude, and it'll give you a good picture of what type of weather conditions you can expect. It gives you the winds at altitude. Not only does it give you the wind direction, but also it gives you the speed based upon the contour interval. In other words, how close the gradient, how tight the gradient is, the winds may be very strong, or if you have a weaker gradient, the winds will be lighter. Remember that the winds blow parallel to the contours at the upper levels. That's what we call the geostrophic wind. So even though you don't have wind barbs, you can estimate the strength and the direction of the wind. So using this, you can pick your most favorable altitudes for wind, meaning that you can maximize your tailwind and minimize your headwind. You can also look at the jet stream charts. That would be 300, 250, and 200 to estimate the location and strength of jet streams and jet cores. That's very important when you're forecasting clear or turbulence. We'll talk about that in another video. You can use these charts also to get an idea of where the temperature profile is, looking for, of course, temperatures warmer than 0 when you're in clouds so that you don't get ice. If you have temperatures colder than 0 and clouds, then the potential exists for icing. Also, you could use the temperatures on this chart to figure out aircraft performance and true airspeed. And then also you can look at the contour pattern to figure out if there are highs and lows. And not all of these charts actually do label H's and L's, but where you have a high or a ridge, typically that of course is good weather, and where you have a trough or an L for low, that usually implies worse weather with lots of clouds, precipitation, and possibly thunderstorms. And they also plot dew point depressions or dew points on this chart. Some sources also highlight areas of high relative humidity. In this particular chart, they start to plot relative humidities greater than 70%. And usually where you find relative humidities more than 90%, you could probably be assured that there are clouds in that location. The last item on our to-do list is looking at sources of weather charts, constant pressure charts. And there are many places where you can get constant pressure charts, but these are probably the best. The first one is the real-time weather data, which is provided by the National Center for Atmospheric Research. Also, the U.S. Government Storm Prediction Center has a great website for charts. And then also Leidos Flight Service, since pilots tend to gravitate towards flight planning software, Leidos actually provides upper air charts. We'll look at all three of these and compare their charts. The first one is the real-time weather data site. If you go to weather.rap.ucar.edu, you'll find this home page. You navigate to the upper air tab, click on that, and it'll give you this website or this page. And at the very top, that's where you can click on the different charts from 925 up to 200 millibars. Use the one that has contours, not the one that just plots the Ray-Wisson data. And from that, you can look at the constant pressure charts. I provided the next few examples, two charts, one from the middle of the atmosphere or lower atmosphere, and one from the upper atmosphere. So here is your 700 millibar chart from RAP, UCAR, and real-time weather. And they use relative humidity on this chart. They do plot the dew point depression, but also they plot the relative humidities to help you visualize where there is clouds. Also, they plot the contours and also the winds, but they don't plot the letters H and L to indicate highs and lows, so you have to figure that out yourself. Here is a 250 millibar map, and this is, of course, in the jet stream, so you can see they use various colors to indicate the strength of the jet stream or isotax. And it looks like the isotax change actually about every 10 knots until you get to stronger wind speeds, and then it's every 20 knots or 100 or 20 or 25 knots. And the strongest winds, of course, are purple, and those would be more than 150 knots. Here's the Storm Prediction Center. If you go to SPC and click on their forecast tools, the drop-down menu will take you to the upper air maps. This is their upper air map page. The top part has objectively analyzed maps. These are the current maps for this particular day. Also, they have the ability to loop the maps so that you can see how weather has changed. And then the bottom part is the archive. So you can go back all the way to 1998 and pull up any particular day if you want to look at what the weather was like. If you were flying on a particular day and kind of curious, you can use the map archive. We're going to look at the top part, the objectively analyzed maps. We'll take a look at 700 millibars and 250 and compare those to the real-time weather site. So this is your 700 millibar map for the same time period that we saw before. And once again, they don't show H's and L's, highs and lows. You'll have to infer that yourself. They do show wind, of course, wind speed and wind direction. They plot contours, but they don't plot relative humidities. They do plot on this map temperatures. Those are the red dash lines. And then also they plot, I think that is the dew point depression that they're actually plotting in green, and it looks kind of messy. Here is their 250 millibar map. They don't have as many colors shading the isotax or the wind speeds. It looks like they start shading somewhere around maybe 75 knots or so, because I can see that winds that are 60, 65 knots are not shaded, but more than that, I see an 80 that's shaded. So it looks like they start to shade, and you can see actually on the side they have a key. On the left side at the very bottom, they have a color key to indicate the strength of the winds. They do not plot a constant altitude lines, what we call contours. Instead, on this chart, they plot streamlines. Streamlines follow the wind. And then if we go to Leidos, 1-800-WX-BRIEF, click on Weather Charts. It'll give you this page, and you click on the millibar charts. We're going to take a look at the 700 millibar chart, which is 10,000 feet, and also the 250 millibar chart, which is 34,000 feet, flight level 340. This is what the 700 millibar map looks like, very similar to the other ones, except they color the United States and also Canada and Mexico brown to indicate that that is land, and also the oceans they plot as blue, as well as the Great Lakes. And you can see on this chart they actually do put H's and L's, which is pretty helpful. They also draw lines of constant height, which we call contours, the black lines. And then also they plot the temperature, the dew point depression, and also the height of the pressure surface. And then you can see temperature lines every 5 degrees Celsius in red. Here is the 250 millibar map from Leidos, and they start shading at 50 knots, and they change the color as the speed increases all the way up to 140 knots. If it's stronger than 140, then they'll color it white. And here you can see also they don't have any dew point or dew point depressions on this chart, but they do have the temperatures, and they're pretty cold and they're pretty bold. They put them in white, and of course everything up there is negative temperatures.